All right, so for section 5 of chapter 11, we finally get to see, you know, some of the operations in space and why we began with the study of vectors to get a decent concept of vectors and how those ideas of vectors are going to help aid building equations for lines and planes, etc., in space. This is an extremely important section, 11.5. So I will take my time because, um, you know, you guys. So right now, they label this class Calculus 3. Prior to that, it used to be titled Vector Calculus. Prior to that, it used to be titled Multivariable Calculus. I understand that there hasn't been a lot of calculus in Calc 3 yet, but these ideas of vector calculus, multivariable calculus, the calculus of of space, we need a really solid foundation of how to think about equations in space in order to start taking, say, derivatives of these functions. So let me start. So the idea, let me start with the goal right now. How do we find an equation of a line in space? Right? So if I were just to randomly draw a line out here in space, how would you find the equation of that line? And I think it's worth taking a second to think about the two-dimensional analog of this question. So let's think back to our algebra class and let's think about what do you need in order to find the equation of a line in 2 dimensions. All right, so if you have some two-dimensional system, and if I just draw some random line here, if you want to find the equation of that line, think about what you need. Well, you need a point, and you need what? A slope. Okay, so if you have a point and you have a slope, then you can form the equation of that line. If you don't mind, I'll just make up something. So really quickly, so let's say you have the point 1, 1, and let's say you're given the slope of 3. So you recall what to do here. You're simply plugging that information, both the point and the slope, into the point-slope formula. And voila, when all is said and done, you have the equation of that line. All right, now let's travel to 3 dimensions. Let's think about the same type of question. How do you find the equation of a line in space? Well, let's start again with what do you need? Well, in space, you are going to need a point, right? A point on the line. And the second thing that you're going to need is a vector parallel to the line. Let's go ahead and move to the next page, and I'm going to try to build this for you. Ready? So recall what I just said on that previous page. What do we need? We need a point on, and we need a vector parallel to the line. So let me start this way. Let's start by, I'm just going to do my best to draw a straight line. And let's label this. Let's label it L. No, let me take that off. Let's label it L sub 1. All right. So line, this is the line that we're interested in. Okay. Now again, we want the equation of this line in space. And let's think back to the things that are required. Well, We definitely need at least 1 point on that line. Now, I'm going to go ahead and say that we have this point right here. This is point P. So I don't know what point that is, but we're just going to label it x sub 1, y sub 1, z sub 1. So x sub 1, y sub 1, z sub 1. All right, and so now let's think about the second thing that we need, which is a vector, right? A vector that is parallel to that line. So, for example, here, this could be a vector parallel to that line. Only I'm gonna make sure that the initial point of that vector is going to be at the origin. So let's actually give that a name. So this vector, all right, we don't know what it is yet. We'll just say it's some A, B, C are the components. We refer to this as the directional vector. And just so that we're all on the same page, those components, the A, the B, the A, the B, the C, we refer to those as directional numbers. All right. So now let's think about how would we proceed here. So I'm going to do my best to draw this vector v and have it be parallel to L sub 1. So this is v. All right, so from this information, how do we build an equation of a line? Well, first off, the type of equation that we're going to build is going to be a parametric equation. So if you have, well, first off, if you were done the injustice of your pre-calc teacher not talking to you or telling you about parametric equations, if that injustice was done to you, my sincere apologies. If you had me for pre-calculus, that would not have happened for sure. But nevertheless, don't worry, I'll get you to where I need you to be. So the way what we need to do is we need to think about some other point on this line, right? Some arbitrary point. Now, we're going to label this point Q. And I need you to understand that we don't actually have access to this point. In fact, this point Q is, let me write it, point Q. That's going to be some x, y, z point. In fact, this point Q is going to serve as a placeholder for every single point that we don't have, right? Because the only access, the only bit of access that we have is this one point. We know one point on this line. Point Q serves as just a placeholder for every other point on that line. And now, let me just go ahead and draw that. So I'll just say for now that this is point Q. Okay. So does it make sense to you that if vector v is parallel to line L, then vector v would be parallel to vector p to q, no matter where q is? it would also be parallel to P to Q. I hope that makes sense, because I need that to make sense so I can proceed. So P to Q I need to make a statement of equality. So please don't drift off on me. Don't you do it. Don't go anywhere. I need you to grasp this. So if P to Q, vector P to Q, is parallel to vector V. Now maybe clearly P to Q is longer than V, right? The magnitude is greater than V. But you would have to agree with me that I can multiply some scalar by V to make it just as long, just the same magnitude as P to Q. So here's the statement I'm about to make to you, right? Ready? So there's some number, I'm going to call it T, because I don't know what it is. There's some number that if I multiply that by V, it will equal P to Q. So P to Q must equal here's that T V. All right. Almost there. So let's go ahead and define P to Q. And then let's get to our equation. Ready? So you know that if you want P to Q, if you want to move this vector to so that its initial point is at the origin, if you want to think of it as in component form, you and I know how to do that. Right, this is right out of the first couple sections. So vector P to Q, well, that's just going to be terminal minus initial. So x minus x sub 1, y minus y sub 1, z minus z sub 1. All right, and so all I'm going to do is I'm going to plug in for V. I'm going to plug in for P to Q, and I'm going to distribute that T. Ready? Let's go ahead and get to where we need to be. All right, we're there. So a scalar multiplied by some vector parallel to the line. Does it make sense to you that if you go ahead and if you distribute this T, and then what we're going to do is we're going to solve. I'm running out of room, but maybe I can. I told you I was going to take my time on this section. Honestly, I could just give you a cursory glimpse of it and say you figure it out, but this is so important that I'm trying my best to take my time. So I do hope that you're along for this ride. Okay, so what I want to do is I want to set each component equal to each other. So if I take this x component, remember I distribute my t, and set it equal to this x component. Let's see if you'll agree with me there. So that would mean x minus x sub 1 is equal to t times a. And then y minus y sub 1, let's set the y components equal to each other, is equal to t times b. And finally, set those z components equal to each other. Okay. So now we're here at the answers. So if you are okay, if you're okay working in parametric form, which I hope you are, so solve for x, right? If you take this equation here, and solve for x, that's where we're at here. Same thing, solve for y. Same thing here, solve for z. This is a parametric description of that line. The t is what we refer to as a parameter. Now, if you have had no exposure to parametric equations, you don't have to be super good at it. I would suggest you can email me, and I have videos on parametric equations I could send to you if you like my style of teaching. If you have another outlet, you can always go to online and find a video on parametric equations, a quick 10-minute video, and you're probably good to go. All right. Now, if you want to get back to rectangular equations, right? So now, if you don't want to stay with parametric equations, then can you, let me see if you can spot this. Can you see how if you solve for t, right? If you solve for the parameter. So in other words, if you take this equation right here, solve for t, take this equation, solve for t, take this equation, solve for t, t is equal to t is equal to t. Therefore, this is this is another way of writing equations of lines in space. So we have what we call symmetric equations and what we call parametric equations. You want to be good with both. But at this stage, no more theory. Let's actually just jump in and try one. Ready? So we're asked to find both the parametric and the symmetric equations for the following. So find a parametric and symmetric equations of the line L that passes through the following point, so that's our P, and is parallel to this vector V. Okay, so that's nice. So in this case, they've done all the heavy lifting for us, really. We already have point P is 1, -2, 4. And we didn't have to find a vector parallel to the line. That was given to us. So V is equal to, remember it's equal to A times B, or I'm sorry, A, B, C for components. And in this case is just 2, 4, -4. Hopefully this shows up okay on your screen. It's a little bit blurry to me. Okay, so ready? Let's go ahead and write the parametric description first. Let's start there. So the parametric description is x is equal to, my apologies, let me see if I have it on a, yeah, so x is equal to x sub 1 plus t times a, y is equal to y sub 1 plus t times b, and z is equal to z sub 1 plus t times c. Okay. So you have everything you need. You know that a and b and c. And what else do you know? You know x sub 1, y sub 1, z sub 1. At this stage, we just plug in. And you're done. So I'll go ahead and do that for you. So the parametric description is x equals 1 plus 2t, y is equal to -2 plus 4t, z is equal to 4 minus 4t. All right, so this is fine. Notation-wise, this is fine the way I've written it. A lot of times we think about this as a system, and you'll see me write it like this. Finally, so we've finished the parametric description. At this, let's go ahead and go to the symmetric equations, and I'll change this color. So for the symmetric, the key is you need to the first thing you need to do is solve for t. All right. So we end up with, if you solve the following equation for t, you get x minus 1 over 2. And then y plus 2 over 4. And finally solve for t, you have z minus 4 over, what is that, negative 4. The only thing left is to make a statement of equality here. All right, so example 1 is done. Example 2 is very similar, only that let's see what information we're given and see how that's different. So we want to find a set of parametric equations, so we don't need to do the symmetric this time, but a set of parametric equations of the line that passes through the following 2 points. Interesting. So you're not going anywhere for a while. Let's think about the two-dimensional analog to that question. So the two-dimensional analog to that question would be, assume that I gave you points 0, 1 and point 2, 3, and I were to ask you to find me the equation of that line. Right? So instead of given a point and a slope, you're given 2 points. Well, you know what you would do here. You would find the slope given the 2 points. And then you would just use your point and your slope to plug into your point slope formula. All right, so plug it in here, solve for y. All right, so that's the two-dimensional analog. I know that you already know that, but it's good to take a step back sometimes before we go forward. So let's figure out how this is going to apply to this question. So let's just label. So let's call point -2, 1, 0. We'll just call that point P. And point Q is 1, 3, and 5. So, all right, interesting. So we now have, you have a line in space, and we know 2 of the points on the line. What we don't know, in this case, is we don't know the directional vector that's parallel to that line. Okay, so we need this directional vector. That's easy to do. All we need to do is just think about point P and point Q as a vector. And then we can simply get that vector into component form. And that would serve as our directional vector. So beautiful. So this is V. All right, and now quickly, now this question, example 2, looks exactly like example 1. In example 1, you were given a point and a directional vector, and you were asked to find the equation. now we actually have 2 points, but we'll take our point and our directional vector, and we'll go ahead and get to it. So I'm going to label A, B, C. We went from P to Q, so X sub 1, Y sub 1, Z sub 1, and finally plug it in, and I'm just going to go ahead and get us to our answer. So X equals -2 plus 3t, Y is equal to 1 plus 2t, and Z is equal to 5t. There you go. All right, so we've discussed lines, the equations of lines in space. The next topic is the equations of planes in space. So I don't have two-dimensional analogs to go to, right? If you know, in terms of prior information that would help you understand the new information. But let me see if I can still build you to where I want you to be. Ready? So let me just draw this. Let's pretend like this is the XY plane. Okay? I don't know why I drew it like that. Let me see if I can draw that better. All right, so this is the XY plane. Remember when life was good back in middle school, high school, before they ever introduced this third axis, right? Life was simple, everything was in a plane. So now my question to you is, think about how, if this XY plane, think about how it would move. If it could move in space, how would it move? Well, don't you agree with me that it would just go up and, it would just go up and down the z-axis, right? This would just go up the z-axis. You could move that plane up, you could move it down, but it would just move up and down the z-axis, right? In other words, it would move perpendicular to the both x and y. So that's important. That's actually an important thing, that the idea that when your plane moves in space, its movement is going to be normal or perpendicular to itself, right? So now let me start with what we need. So if you want to build an equation of a plane, here's what we need. First thing, we're going to need at least 1 point in the plane. All right, so I'm going to kind of call on this picture here. So this point P right here, I need to know at least 1 point in the plane. And since the planes are going to travel perpendicular to itself, I'm going to need to know whatever vector this is that's normal to the plane. So I need a point, and I also need a vector. And this vector we require, we'll call it, instead of calling it vector v, we'll call it vector n, because we need this vector to be normal, perpendicular to the plane. All right, that's what we need. And now let's figure out how do we finish this up. So just like in the previous problem, we'll assume that point Q, we'll call it x, y, z. This point Q, this is right here, this is some other point, right? Some other point in the plane. I don't care where it is, because it's an arbitrary point. It represents all the other points that we don't have. And here we go. We're going to need to we're gonna make use of a topic that we learned in 11.3, which is the idea of the dot product. So do you agree with me? Do you recall that if you take the dot product of two perpendicular vectors, remember the dot product is always 0. So what does that mean for us? So that means if you were to take P to Q as one vector, and I'm actually going to write the n first. Give me 1 second here. That means if we start with vector n, and you take the dot product of n with this vector P to Q, we already, since we know that they're perpendicular, we already know that it must equal 0. That's the key point. And now the rest is easy. Let's just plug in, just like before. Let's plug in for n, let's plug in for P to Q, and then we're all done. So I already have n. Oh, I'm so sorry. I already have n defined for us. Let me just go ahead and define P to Q. So in component form, that's going to be x minus x sub 1, y minus y sub 1, z minus z sub 1. And here we go. Let's plug in for P to Q. Let's plug in for n. All right, at that point, you got take the dot product, and you have your equation. So my hands are too big for the stylus. That's what keeps happening here. A, B, C. Let's dot that with this P to Q. All right, easy enough. I'm going to go to the next page and I'm going to produce this answer. If you take this dot, right? Remember it's x components times x components, y times y components. You get your equation of a plane in space. So this, it's just a language is important here. If it's solved for 0, that's what we call standard form. If you let me restate that. It's not solve for 0. How do I want to state that? Well, with you could distribute the A, distribute the B, distribute the C, and then combine like terms, right? Regroup and combine. So let me just restate in its current form, this is what we refer to as the standard form of equation of a plane. If you go through the process of distributing all that out and combining like terms, you can also produce the general form. No more theory. Let's just try an example and then we'll take a break. All right, so it says find the general equation of a plane containing the following points. So this is what we want when we're all is said and done. All right, so what we don't have, well, let's start with what we do have. We have a plane and we know 3 of the points in the plane. Now let's go with what we don't have. We don't have the vector that is normal to the plane. Ready? So let's just label point P 2, 1, 1. Let's label point Q 0, 4, 1. And I'm just gonna let's just use M will be negative 2, 1, 4. All right. So if you follow me to my picture over here, I can if we think about P to Q. All right, so this is point P, this is point Q, and this is point M. So let's just think about the vector P to M and the vector P to Q. Now, do you agree with me? Do you agree with me that if you take a cross product, you get a vector that is perpendicular to the 2 vectors you have, right out of the last section? So that's exactly what I'm about to do. I want to, let's form P to Q. Let's form P to M. All right, I got to start to pick up the pace a little bit. And so I think you can follow me with how I did this. And since what we need, right, the thing that we're missing is that normal vector. That's what we don't have. Well, I can get a vector that's normal to P to Q, P to M if I just use the cross product. So I'm going to go ahead and write that. So if I just take the cross product of P to Q, P to M, that's going to give me a vector that is normal to my other two vectors, and I'm just going to produce this for you. So without showing you the steps. So here it is. N, the normal vector, is 9i plus 6j plus 12k. All right. So you know where we go from here. We need, so N is 9 component form, 9, 6, 12. So I got A, B, C. I also need x sub 1, x sub 2, I'm sorry, x sub 1, y sub 1, z sub 1. So let me do that. So I started with point P. So this is going to serve as my x sub 1, y sub 1, z sub 1. That's it. You have everything you need. To go into this form right here. Plug in for A, plug in for x sub 1, and so forth. So let's do that. So that gives me 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1 is equal to 0. Now, if they asked for the standard form, we would be all done. They did ask for the general form. So all that requires is that you distribute it out and combine like terms. So here would be the general form. So 3x plus 2y. I think, my sincere apologies. I think I should be 9x plus 6y plus 12z minus 36 equals 0. There's your solution. It's sometimes it's annoying. If you were to look up a question like this in the back of say a textbook, since they would have noticed that 3 goes into 9, 6, 12, and 36, they would have divided everything by 3. But nevertheless, you're done at this point. All right. So thanks for sticking with me. I know that this is, this can get tough. So anyway, hats off to you for sticking with me. Stay with it. You got this. I will see you in, we're not done with 11.5, but I'll see you in part B of 11.5.